So continuing on with some volume formulas, and we're going to take a look at a principle called Cavalieri's principle today. We are starting off with some general cylinders. Cylinders, remember, they have two bases, parallel bases. And we look at this first one and we can consider it a rectangular prism, typically flat surfaces such as squares, triangles, hexagons, we call those prisms. For anything that is circular, we would call that a cylinder. Notice that they have the same volume formula. So you have big B times H. That's what you find on your formula sheet that is given to you for the Regents exam. Your job is to determine what we fill the big B in with. Big B standing for base area. So what we have to ask ourselves is, what's the shape of the base? So on this picture, the shape of the base is a rectangle. So we are replacing that big B with our rectangle formula of length times width. In our second picture, our shape of the base is a circle, and we're replacing the big B with our area formula for a circle, which is pi r squared. So looking at some of these shapes below, considering that formula, we're going to find the volume of the following figures. So our first one we have is a triangular prism. Triangular prism being the shape of the base is a triangle. Okay, so in general, our volume formula is big B times H. The big B is standing for the base area, and since the shape of the base is a triangle, we are replacing that with 1/2 base times height. Now notice we have two heights. These are different. Okay, this is the height of the triangle, where this is the height of the prism, or the distance between the two bases. So when we're filling this in, you have to be careful with what that H stands for. Okay, so we have 1/2 looking at the triangle, that's the shape of our base. So right now all of our information is coming from there. Our base and our height measured with perpendicular lines, we have 19 times 24. Now for this height, the height of the prism, the distance between the bases, I want to see what's that distance between my two triangles, and that's going to be 47. Okay, so the nice thing with this is we can plug this all into your calculator, and once we do that, get a final answer. We're going to have 10,716, and now our label in volume is going to be centimeters cubed. All of our units will be cubic units. Okay. Over here, we have an oblique because notice it's not standing straight up and down, an oblique rectangular prism. So the volume formula is still the same thing. It's still big B times H, and we've called it a rectangular prism because the shape of the base is a rectangle, and I can see that on the bottom here. Okay, remember two and only two sides that are congruent, so that's at top and bottom, so I can show you that's going to be length times width, and then the height is going to be, again, that height is the distance between these things. Now, keep in mind, our distance is always measured with a perpendicular line. So that's why they've drawn this out here on this side. Okay. So this being a length of 17, not our height. It's not perpendicular. Our height that we actually need to solve for is this. That it forms a nice right triangle. And so in order to solve for the height, we're going to do a little Pythagorean theorem. So we're going to have our height squared plus 3 squared is going to equal 17 squared. Okay. 3 squared is 9. We're going to subtract over that 9 from that 17 squared, and we're going to have our height is 280. And then if I want to find the height, we have to square root it, and our height is going to be somewhere around 16.733. Now notice it says round to the nearest hundredth, so I don't want to round until the very, very end of our problem. Okay, so now we can come back over here to the bottom and start to plug things in. I need length times width of the base. So again, our length and our width of our base, that's 5 times 5. And the height that we just found, 16.733. And again, we can plug that all into the calculator. And when we do rounding to the nearest hundredth, we're going to get about 418.33 label inches cubed. And on the bottom, we have a cylinder. Again, it's an oblique cylinder, meaning it's shifted over. It's not, the bases are not going perpendicular. I should say this this side here, our lateral edge, is not perpendicular. So again, our basic formula, starting off, big B times H, we replace the big B with the area formula for the shape of the base. Shape of the base is a circle, so we have pi r squared. That's the area formula for your circle. And then the height we have has to be that perpendicular height. And we don't have to find it here. They actually showed us our perpendicular height. This is our height of 15. It's perpendicular to our base. Okay, so we can plug this in. So we're going to have pi times your radius of 5 squared times the height of 15. And if we were to multiply this out, a form that they could ask us to leave our answer in is either exact or in terms of pi. If we were to do that, that's saying take our 5 and square it, we get 25. Multiply that by 15, and we get 375. Then I could attach the pi. So this would be called either exact or in terms of pi, and I could label that with centimeters cubed. Since the question said rounding it to the nearest hundredth, we're going to actually plug this all in and get 1,178.11 centimeters cubed. Okay, on to the next page. Talking about Cavalieri's principle. So this is a principle that is connected with volume, and it is stated that given two solids that are included between two parallel planes. So the way that we can tell they have parallel planes is typically because they have the same height. So there's some flat surface here that these coins are situated in between, both on the top and on the bottom. Okay, so we have two solids that are included in between two parallel planes. If every plane parallel to the two planes intersects both solids in a cross-section of equal areas, then the volumes of the two solids are equal. Okay, so things we have to check for. We have to see, do they have the heights that are the same? That gives them the parallel planes. Are their cross-sections going to have equal areas? So if I take a look at all of these things, cross-sections, remember those are going to be parallel to the bases. So when I take a look at the cross-sections, do they have equal areas? If they do, then the volumes are going to be equal. So looking at that, connecting it to this, it says given two stacks of quarters, as pictured, what do we know about their volumes? Okay, well, I know that the quarters right now, we can see that they have an equal height. So first off, they have equal heights. So that's telling you the parallel planes, right? So they have equal heights, and they're all quarters. So I should know all cross-sections all cross-sectional areas are going to be equal because they're all quarters. So every time I take a quarter and I take the area, they should always be equal. So I have equal heights, and all cross-sections have to be equal. So what do I know about their volumes? So then I can say, so the volumes must also be equal. And if I had to justify why, if somebody said to me why, well, it's because of this Cavalieri's principle. So what we're really looking for here, if you ever do apply this Cavalieri's principle or think about this in terms of volume, I want to check the heights, make sure they're same. Check the cross-sectional areas, make sure that those are the same. As long as that's all the same, then the volumes of the shapes will be the same. Okay, so that was dealing with some prisms and cylinders. We're going to look at volumes of pyramids and cones, so objects that have one base. So we've looked at this before with the slant height, that's that height on the outside. That's different from the actual height of the pyramid or cone. The actual height of the pyramid or cone, keep in mind, is always, again, perpendicular to the base. It starts at the vertex and goes down perpendicular somewhere to the base. Okay. Pyramid typically will have some sort of a polygon for a base, where your cone is going to have a curved a circle for the base. And a sphere is a ball, and all we have to do, the only variable that we have for that is our radius. So if we try and apply the volume formula to these, now again, on your formula sheet, what you will be given is volume is equal to 1/3 big B times H. So the only difference between a pyramid and a prism is this 1/3. Big B still representing base area. So in this picture, since the shape of the base is a rectangle, I know that big B is replaced with length times width. And then we have our height. So filling this in, I have 1/3 the length and width. So I have 9.5, my width of 8, and my height measured perpendicular to the base of 9. Okay, so again, this problem, very nice and easy. I can plug this onto my calculator. If you're not a huge fan of the 1/3, you could option multiply all of these out, get an answer, and then divide it by 3. Okay, so double check this on your calculator. Make sure that you're entering this incorrectly. Total volume at the end should be 228. Again, label centimeters cubed because you're dealing with volume. Okay. If we're looking at the volume of the cone, again, volume because it's a cone comes to a point. We now get that 1/3. But again, it's going to say big B times H. And we replace that big B with the area formula for a circle, which is pi r squared times height. And our height, even though this is kind of an oblique cone, our height is still labeled for us and measured with a perpendicular line. So I can still enter in all of the information. I have pi times my radius of 3.2. And then the height, which is provided, of 5.8. Now, notice it's saying here in terms of pi. So what does that mean? It means in our calculator, we're going to type in 3.2 times 5.8 times 1/3, and don't touch the pi button. So we multiply everything except for the pi button. And when we do that, now we're going to get something that looks like 19.7973 and a big bunch of threes, 3 repeating. And I could attach the pi to the end of this. So this would be our volume in terms of pi, labeling it meters cubed. Now I could round this if I wanted to, maybe nearest 10th, to tell you it's 19.8 pi meters cubed. Okay. So number 5 is going to be a little bit more challenging. 1, there's no picture. 2, it's a triangular base. So we have a pyramid with a triangular base. So let's say that that's the shape of our base. And it's equilateral with sides measuring 4 feet. So all sides of my triangle are equal. Okay, and it tells us that the volume is 64 square root 3 feet cubed. We have to find the height this time. Okay, so keeping in mind our volume formula is 1/3 big B times H. That's what we're given. Shape of the base is a triangle. It's telling us it's a triangular base, so that means I'm replacing big B with 1/2 base times height. That's the formula for the triangle. I multiply that by the height of the entire pyramid, which is actually what we're trying to find. So this H will stay H. The volume, well, they've given us the volume. They've told us that that is 64 square roots of 3. So I'm filling in what I know right now. The other thing that we could fill into this formula is this B, the length of the base. The length of the base over here is 4. What we don't have is the height, and we need to find that height. Okay? So because this is an equilateral triangle, we know all of our angles are 60 degrees. So if I have to find this height of the triangle, I could do a little trig ratio. I could do some tangent. So I would have an opposite side for the height. I'd have my adjacent side, but now keep in mind, because this whole length is 4, this will be split up into 2. So if I take a look at this triangle, that's the triangle that we're doing our trig value in. We have opposite, we have adjacent, we're going to use tangent. So we have the tangent of 60 is equal to opposite over adjacent. And when we cross multiply this, we can solve for H. And we're going to be able to find H. Again, plug that all in your calculator. We're going to find H is about 3.4641. Okay. So what that's finding is our height. Now we can plug this into our formula over here. 64 square roots of 3 equals 1/3 times 1/2 times our base of 4. Remember, you want that whole base. Times the height that we just found, 3.4641. And the height that we are actually trying to find Okay, so at this point, I can enter all of this into my calculator and get a value. And when we do, I'm going to get something around 2.3094, trying to find that height. So if I divide through by that, 2.3094 on each side, what we're going to get is our height. And our height is about 48. And now just be careful here. If we're finding a height, a linear measurement, it's just going to have a label of feet, 48 feet. Okay. The very last thing that we are going to do is take a look at this one. Now we have to compare two shapes. So it says, suppose you're filling a conical, meaning a cone, paper cup with a height of 6 inches with water. So we have a cone. The height of this thing is 6 inches. So I measured this with a perpendicular line to the radius. I know that that's 6. And it says if all of the water is then poured into a cylindrical cup, so cylinder, so can idea, with the same radius and the same height. Okay, so that means the height here is, again, still going to be 6. And the radius, well, I don't know what the radius is back here, but whatever it is, it's got to be the same thing over here. And it says, to what height will the water reach in the cylindrical cup? Okay, so if we're thinking about this, our volume formula is 1/3 big B times H, where the big B is going to this time be pi r squared because it's a circle. And then our height we actually have, it's a height of 6. So if I were to simplify the volume of the cone, 1/3 of 6 is 2 pi r squared. That's all I know right now. And we're going to do the same thing for the cylinder. The only difference here is it's just a big B times H. I don't have the 1/3 in front. So I have pi r squared times a height of 6. So the volume of the cylinder is going to be 6 pi r squared. So if I look at the two of them, I should be able to see a difference of 1/3, which should hopefully make sense because our original formulas, the only thing that was different in these formulas is a 1/3. Okay, so I can tell you that the cone is going to be 1/3 the volume of the cylinder. Okay, so if that's the case, and I know that I could fill the cone up with 6 inches when a 6-inch height of water, that means it's only going to go about 1/3 the way in the cylinder. So if I have 6 inches and I take 1/3 of that, that's going to give me 2 inches. So I can tell you, all right, what height will the water reach in the cylindrical cup? It's going to reach a height of 2 inches. So that's a little bit of volume, a little bit of applications with volume. We're going to keep working with this. Just make sure that you're aware of the formulas. If you have any questions, please come in and ask. Have a great day.